Okay, I think it's probably time for us to get started. So howdy.
Howdy.
My name is Jian Tao. I'm an assistant professor from the School of Performance Visualization and Fine Arts. I'm also assistant director for project development at the Institute of Data Science. So I have been teaching short courses at HPRC for 5-6 years. Before I joined the Department of Visualization in 2021, I was teaching multiple courses, more than 5 probably at HPRC. And after I switched to a tenure track position now, I start just teaching 2 or 3 every semester, every year. So every semester actually. So today we're going to get a little bit introduction of CUDA programming. And CUDA is kind of like a C and a C++. And there are only some small modifications, as you might see. It's just mostly we are learning the library, how to use the library itself. But the language itself is just C and C++, mostly C++. With that, let's get started. So today we'll have 4 parts. The part 1, I think, of 4 parts, and we'll have a short break. I think, probably just 2 hours, 2.5 hours. We can just take 1 short break in between. The first part, we'll get started with Grace, which is one of the working cores here at HPRC. It contains, the system itself has many GPUs, and you'll see on HPRC's website. And secondly, we'll talk about the GPU as an accelerator. It's nothing more than an accelerator, actually, for most of things we're doing here. We don't use GPUs for visualization, at least for the stuff we're doing using CUDA mostly. You can still use a CUDA for visualization purpose, but it's not a primary goal for the CUDA programming language. Now, part 3 will run CUDA on Grace, get you all started. At least, where we get some simple program started. I'll show you how to submit jobs and do something like that. We haven't done this in-person training for a while for GPU programming, and this is probably one of the first times in a couple of years. So it's good that we get people in person, and then we can get you started, get your hands dirty. The last part, we'll go through some details about CUDA. And even though it's a 2-hour session, we only reserve like half an hour or 15 minutes for CUDA basics. But as I'll explain why, and you'll see my point. So first, we'll get started with the working environment, trying to learn how to get you all started on HPRC systems. If you have a computer with NVIDIA GPUs, with a CUDA supported, you can directly run stuff on your GPU. I have a Mac here. The Mac Silicon is working well. It's actually, I can run CPU, GPU all together with my MacBook, as long as you get the right compiler setup. But if you want to run any CUDA program, you needed to have a NVIDIA GPU card. Fortunately, AMD and Intel, they're both working on different software packages help you to convert CUDA into their own platform. So as long as you get familiar with CUDA, convert that CUDA to OpenCL or ThinkCL or many other different platforms should be straightforward. There have been tools out there for you to do the conversion. So learning one, and you can easily get adapted to many other different similar but kind of different platforms. So I put in a button here, I believe. Did we share the slides with all the attendees or not yet? Okay, so it's fine. I'll share the slides because every semester when I give this new short course, I'll update some stuff. So the slides will be different, a little bit different. So HPRC portal could be found if you get to HPRC website. There's a portal button, menu button to the very left. I'm sorry, very right here. And you can see there we have multiple systems, and Grace portal is accessible through VPN. If you are not on campus, you needed to get in VPN. And actually, VPN had some problem in the last couple of days. I had trouble, but I think they fixed it today. After you log into the Grace portal, there are multiple menus, but the one that you will find it very useful is to use this Grace shell access. And you can also use the file menu that will give you direct access to the file structure on Grace. You can directly, I'm not sure we can do the drag and drop, but you can easily copy files, download files, upload files with that interface. If you're not familiar with the command line interface, that will be very convenient. And then after you click this button, Grace shell access, I'll go through this procedure with you all quickly. You'll get to this, and just like a normal system, whenever you get log on any servers on campus, you'll see something like this, very similar. You need your net ID and also your credential. And since already, if you can get access to the portal, you should already have the TAM credential authorized. And then you just need to do the dual push. And that's what I set up with my cell phone. And after that, you get into the system. This is what the system looks like. It will give you some important policy information at the very beginning, and it will show also how much disk quota you're using, because it's a shared system. Everyone has a small quota, not small, but I have 10 gig files for my home directory. I have one terabyte of high performance disk for my scratch space. Everyone has probably different quotas, because depending on your status and your request. For students, I'm not sure what's the maximum. After you log in, you'll see if you already have an account on Grace, you'll see your quota there. And also you can show the quota during when you're on the system. You can type show quota to show whichever files. It's kind of when you're using Conda or installing Conda, some other packages, it's very easy to exceed the total file usage. That's a number of files you can put in the system. Sometimes it's kind of easy to go beyond that file usage, but you can always send an email to IT support at HPRC. They can help you to increase the limit, as long as you can justify your request. So these are a couple of commands. With this, I'll switch to the portal side. We'll go through this quickly all together. So first, I get to portal, and what I'll do, I go to the Grace portal, click here, which will lead me to the Grace portal site, since already logged in my TAMU credential. If you click the file here, you can go to your Scratch USA, your directory, or your home directory. If I go here, it will lead me to my home directory. And with this interface, you can upload and download files to the server. Make it very convenient. You don't need to do SCP or other things, which some people might not be convenient with their terminal command line. For the cluster, you can get to the shell access, which is a web-based shell. Let me increase. If you're on Mac, you can use a terminal directly, like the one I'm showing here, which is a Mac terminal. If you're on Windows, you can use a Windows terminal. Or you can do, it's already on Grace. I switched out, but it's all right. So I'm getting back to the web-based interface. It's asking me about my password.
Mac terminal, you need to SSH to.
Exactly, SSH to grace.hprc.tamu.edu, and that's how you get to there. But since we're not getting through the terminals this time, and ask me for my credential, I do this push. There we go, and that's it. So now, something probably you can learn from other tutorials, and you can get to online YouTube videos to check out the details. But under my home directory, I created this shortcut myself. What I did, I just ln-s. It's a symbolic link. I create this. What I did, I just scratch. I create a local directory called scratch. I'll copy it as scratch one. So what I did, I'm sorry. Scratch one. Let me do this one more time so that you see. So there is a system environment variable called a scratch. SCRATCH. So scratch is pointing to your scratch space. Since it's a shared system, everyone has a very small quota for the home directory. You can do show quota. Like here, it's limited to 10 gig. 10 gig is big, several years ago, but now 10 gig is very small. If you run some big language models, just one file can easily go beyond 10 gigabytes. So it's recommended that everyone use the scratch space. Scratch space, it sounds like scary, scratch, but you are supposed to be able to use it for about a month without, as long as you keep your file there, for a short period of time, you're safe. No one will touch your file. But if your file go beyond a certain period of time, once in a while, the system will purge, clean up the scratch space for everyone else. Just consider it's a scratch space. For you do the calculation, you're supposed to be copy your data back to your home directory or download it to your servers or to your local laptop or computer after you're done. So that's a so-called scratch. So it's probably easier if you use this scratch. It will already created for you, CUDA to get to your scratch space. And let's go back to the slides. That's already where we are starting here. So we have all the exercises for this tutorial, and this short course have them this file under scratch training CUDA.exercise.tgz. And what I did, I just copied it to my scratch space, and then I just unzip it. R, ZXVF, it's just the option for me to unzip my file and untar it. And then I just show all the details for this, this ZXVF. Basically, that's the options for me to do the unzipping, if you are familiar with that. And then you'll see a directory called CUDA showing up. And then you see it there, and you see the directory, and you start doing your work. So let me go back to the slide, my terminal. So what I will do, since I already have this file, let me just remove it, just to repeat everything you all did. Oh, so assuming I have nothing here, what I did, I'll copy from scratch training. I use a tab. It will auto complete the command. So that's why I like like typing fast. Actually, I'm just using the tab key. You can copy this to your home directory, current directory. Dot means your current directory. That's where I am. If you do the tab pwd, the print your working directory, that's where you are. And basically, that's the directory that I'm copying my file to. And then if you do ls, you'll see this file appears. I do tar zxvf CUDA. So that will unzip. X means extract all the files from this table. And then V means verbose, file means showing all the files. That's what I got. You can see this file showing up here. You see a directory got created called CUDA. You see it there. There is a README file. I believe it's updated. And I'll see this hello world, like any other program language. We will start with hello world. Now, the next thing you need to do. Currently, it's a if you do the ML, which is module load, you can check your modules already loaded on this system for you, because it's a shared system. Everyone has different requirements for the software. So we have a software environment management system. And this management system will manage all the software environment you want to use. Every time you want to set up some software environment for yourself, you need to load the modules you need. There are so many packages installed on this server. Many of those you might not need it. You don't need it at all. So for this particular, for CUDA, you can do just simply CUDA, which is not recommended for experienced users, but for beginners, it's completely okay. The reason is that CUDA has multiple versions. If you do this ML CUDA, this will load the latest version for you. Sometimes if you have a code written for, say, CUDA 10, it might not be working with the latest version. So even though it's, CUDA, NVIDIA is claiming everything they have for the latest version of CUDA is backward compatible, but sometimes either the code has some problem, it will crash, or there was some performance loss because you didn't do any optimization for the new architecture. So it's recommended every time when you want to run some code, just specify not just the CUDA, but also the version number. This course is not about that. You'll learn more about how to load modules and other things following other videos. But here, I just want to let you all know, for CUDA, ML CUDA should be sufficient to get you started with the latest version of CUDA you want to use. Okay. So it effectively loads like CUDA compiler? It will load CUDA compiler, CUDA libraries, everything will be in your path. Otherwise, NVCC here, let's see, NVCC here wouldn't work, but now it's trying to find this file. The one more thing I think a little bit beyond time, but one more thing I want to emphasize: not every login node on Grace is equal, is correctly equal. we have multiple login nodes, 5 on Grace. 2 of them don't have GPU cards in it. They are designed just for serving regular users without GPU requirements. We have 3 nodes with a GPU, different GPUs actually. If you want to use a GPU, you have to log in those 3 nodes. Fortunately, I mean, today I'm lucky. Sometimes when I'm logging in, the system automatically put me into, say, Grace 4, Grace 5. Those are 2 login nodes we don't have a GPU in there. But today I'm lucky they got me into Grace 1, which means we have a GPU. But if you got onto Grace 4 or Grace 5, what you do, you can do the SSH, Grace, say, 2, let's see. You need to do type in your password and log in yourself into Grace 2. You have to do the same procedure again, but that will guarantee that you'll have access to the GPUs. The reason is that we have multiple users, many users on campus, sometimes hundreds of users online at the same time. We have a front end to do the load balancing. So we don't want all the users logging one node, right? We distribute them across multiple login nodes. They can all work together. And if you're someone, a system gets you onto Grace 4 or 5, you need to switch to 1, 2, 3. Grace 1, or Grace 2, or Grace 3. Okay. So let me just get back to Grace 1 to ensure that NVIDIA works for you, NVIDIA GPU and CUDA works for you. There is a one command called NVIDIA SMI. This is what I usually do for checking the card on it. So currently, as you can see, we have where's the card here. We have NVIDIA. What's the name? We have CUDA 12. But what's the card? It should be a card name somewhere. It's not showing up here. So if you do this, you can see actually it's a memory usage here. It has 40 gigabytes of memory on this front. No one is kind of running anything. It's kind of too early. Everyone's probably not ready for the job submission yet. So this front, the node is empty. No one's using it here. No process is running. And it has 40 gigabytes of memory. So this command is called NVIDIA SMI, which is a very convenient command for you to check status of the GPU. If you log in the node and you notice some problem with your job submission, running job, if you do the job submission, we'll talk about that a bit later. But just for running on this login node, you want to double check if your GPU is working, or if someone else is using it like intensively, you might have some trouble. If you want to use say 20 gigabytes of memory on the GPU and someone else is running a big job, you might get into some trouble. Okay, so now we have NVCC, which is an NVIDIA compiler already loaded with ML CUDA. And next thing we do, we just need to compile it. It's, if you just want to run it, you can simply do command line, say NVCC hello world, say device. I'll show you what that is in a second. But what it does, it will compile your code, and you get an output. Of course, you can use a -O to rename it to rename your executable. But the default executable is a.out. So just for convenience, I don't want to just get into the long command line. You can always add a -O with many other options and options for compiler, many options. We'll learn a bit more later today. But by default, the executable will be named a.out, which is the standard name for all the Unix Linux systems. To run it, because it's already executable, to run it, use a // basically that tells the operating system, you want to run this file is only your current directory. When you run it, it'll give you hello world. This one is actually calling a function from the device, the GPU, and get it back to you and print out this hello world thing. So if you can get this done, although you can follow through this, you are all done with the initial setup. You get yourself started. Okay. Let's get back to a little bit over time, but I think it's okay. Usually this part is very important for you all to get started quickly, especially for beginners. And if you have never used our system, getting to system submit jobs, it's not easy. You need to spend some time to learn how to do it. So I already showed you all how to do this quickly. Just load, CUDA module and compile it and run it. And basically that's it. Okay, let's jump into part 2 of this short course. So first, GPU is nothing more than an accelerator. It's just something can speed up your calculation, like what most people are using. I bought a 4090 RTX 4090 just not so long ago. It's cost me, well, not me, I mean my grant, like it's a $1,300 on Amazon, and it's a huge disk, huge card. I bought a PC myself, and for my own usage. I specified the power, all the power is fine, but except the length of the case is just too small. That's GPU card like this big, that's 40 millimeters. It's much larger than a regular card. So the latest 4090 card, RTX 4090 cards are using this new architecture. It's kind of A100 chip. It's not exactly the same, but it's the same architecture. So the one I'm showing here, it's probably an older one, it's A100, but the latest one on the server class GPU card, Tesla card, is a H100. So you already read and heard about this. Extremely fast for large language models and many other machine learning training jobs. They're optimized for those. And NVIDIA, if you are following the stock market, NVIDIA price, the stock price like shooting up like crazy recently, just in the last 7 months. So essentially, when you have a computer, there are two main computing devices. If you have a GPU inside, of course you can have FPGA, some other things for computing purpose, but mostly for most people, you have CPU, GPU for your computation. You can also have IPU or DPU. There are many other different accelerators, but today we'll be focusing on just GPU here. NVIDIA, the latest one I just mentioned, H100, is a new called Hooper. I believe it's the full name. It's H100 with 80 billion transistors. For the previous generation, I believe A100 has about 54 billion. So just in a couple of years, they increased the new technology, increased the number of transistors. It's following Moore's law more or less, and it's using the TSMC's latest 5 nanometer processing. I believe it's called 4N, but it's a 5 nanometer process. And now the companies like TSMC is focusing on 3 nanometer technology. The reason I get to know all this because a couple of days ago I attended this Texas Semiconductor Institute conference. AMD recently got a big grant, more than $200 million, to start a semiconductor institute. And a lot of research will be focused on getting the new technologies developed just to develop the semiconductor business here in the US. And Austin got more, but here Texas, we are leading the nation in the way how in the amount of revenue we generate in semiconductor business. That's why the congressperson who wrote this bill actually was from College Station, Bryan district. So he's really pushing this hard, and the state is really following up and getting a lot of money into this flagship university like us and Austin. So UT Austin. So we are looking into this, and my research is not directly involved in the hardware, but we do digital twins and all the things related with workforce training and other things, which is actually a problem here in the US to develop a workforce for semiconductor business. Anyway, so that's the H100, the picture I'm showing here, I believe it's faster. It's not an ASIC. Even though the H100, we are going to have probably about 30 H100 cards on our systems in the near future. It's called ASIC system, which is funded by Natural Science Foundation. $5 million for the hardware and extra $5 million for supporting other things. But faster, it has the same system, has the same architecture as an ASIC. And this picture, I believe, is faster. It's already there and running, but we don't have H100 in this particular cluster. It's a testing and developing system with different kind of accelerators. And you can check it out on HPRC website. So, GPUs, as you probably know before, it's mostly used for showing things on your screen, right? It's take the information from the CPU and other, part of your computer and just visualize it, show it on your screen. That's what the GPU was designed for. But NVIDIA, they figure out a better way to use GPUs for computing tasks. That's how they got really, really, big nowadays in the deep learning community, AI, machine learning, all this kind of stuff. And this shows like overall, stack of systems that NVIDIA they are envisioning in developing. So first they focus on hardware. That's what they're really good at. So NVIDIA itself started as a hardware company selling GPU cards for gamers. And then they started doing a bit more on the software side. Actually, CUDA is one of the main things that are pushing hard as the platform on top of the hardware. With that, they develop multiple things. They have a team developing compilers for Fortran, C, C++. They have a team developing wrappers for Java and Python, and they have also different units at NVIDIA developing all the software stuff for their hardware. On top of the programming language ecosystem that they are building themselves, they're developing multiple libraries. That's really, really the thing pushing this NVIDIA to the very forefront of AI and machine learning. The reason, there is one reason why not so many people attended it, because back like 5 years ago, this was a whole full house. When we started teaching CUDA, everyone's trying to learn CUDA. But now, not so many people want to learn CUDA because all the libraries are there are just really matured and getting really, really powerful. All you need to learn, just learn how to use Python code to call those libraries. You don't need to learn to do CUDA unless you want to get into NVIDIA to develop the software based on CUDA. If that's a goal. But for most of users like me, even though I'm teaching CUDA here for several years, but I haven't written a single CUDA code in the last 3 or 4 years. Production code. For testing, definitely I write some code, CUDA code just for testing, but not for any serious work. The main reason is CUDA is hard, okay? And the libraries are so good. They have like dedicated teams, like probably tens and hundreds of software developers at NVIDIA, top students like you guys. If you get to NVIDIA working there, getting there, they'll be dedicating their time just developing all the software, doing the optimization on a daily basis. There's no way that we can compete against them. That's dedicated team. They know all the hardware details and they can optimize their code to some crazy level and we can never beat them. So the libraries are the things you probably want to spend more time to learn instead of CUDA if you want to do something on the research side. Unless you really want to develop something new, brand new, based on CUDA itself. But on top of that, you can build multiple GPU applications. So you can write your code directly using libraries, or you can write your code directly using the compilers, like the CUDA, directly. And it's just your choice. I'll get into some different programming models and strategies you can adopt. So given the application, this is a very generic scenario that everyone might, it's very straightforward to follow. In most cases, on a computer, no matter what, how powerful this GPU is, the major control is on the CPU. CPU is still the master, no matter what. At least for now. NVIDIA has been developing this CPU, GPU chips on the same die. You probably already know what they're doing. AMD is doing the same thing. But essentially, the main logic, business logic, should be sitting on this CPU. So CPU is the one talking with the rest of the world. And the GPU here is more or less like a system. There's no operating system running on GPU because it's not designed for that. It's designed for mass throughputing, for doing all the computational intensive stuff, but it's not good. It's not designed to handle long instructions. That's like what CPU is doing. So CPU is still doing a very good job. Our machine is getting faster and faster because CPU is getting better as well. And GPU is helping us to do a lot of compute intensive tasks. So for given an application, this is more or less like the general overflow. For a given application, the majority of the task is done by CPU, even though, that's how you define majority. Majority, I mean, the main business logic is followed into GPU, but there's a part of code requires a lot of computation. This part of code might be taking 99% of your computing time if you're running it on CPU. That's what you'll be doing with CUDA and all the libraries. You offload or outsource this computation to GPU and use GPU as a system to help you do this computation. And this offloading could be done in a synchronized way or asynchronous way. In the sense that you can give this kind of task to GPU, and then you can continue doing all this, if there was no dependency for this computer, or in many cases, you need to depend, you need the results back from the GPU for it to continue. But in some cases, you can just send this task with GPU, get it work, or, finish all the job, but you continue your logic. So CPU and GPU that can work all together. That's the most efficient way, an ideal case. But in many, many cases, your CPU could have to stop here, wait for GPU to finish this task, and then it will return back to your CPU, and then you'll continue. So your CPU will be just idling here in many cases, which is not the ideal case, but that's a reality. In many cases, you have to wait until GPU finish your job, and your CPU can do things. One way to do it is to do multiple threading. You can have one thread controlling the GPU task, because the GPU doing all the work, you're doing something else here on the CPU. That's your design. That's your, depending on what your application can do. But in many, many cases, people are trying to figure out ways to divide your task into big tasks and small tasks. You can have a big task here, computer intensive, running on GPU, and a small task, not so computer intensive, running on CPU. So everyone will be happy, and your machine keep busy, and you get your maximum benefit from your computing devices. So it's, best idea is very, very simple. It's just like figure out which part of your code is most computing intensive, and then offload it to GPU, and that's it. Everything we'll be doing with CUDA is just doing all about this. So this is a pretty high-level programming, strategy you might adopt if you want to develop large-scale simulations code. If you're just developing a single node code, all you need to worry about probably just threads. How you can control your threads. It's just share all the memory in one process, and everything is easy. But if you're talking about writing parallel code, you want to consider how to do the communication between multiple processes. Each process will have its own memory, has its own control of everything. But you need to figure out a way to communicate with another process, so that all the processes can work together, nicely. So this is a very simple diagram showing how all the nodes, computing nodes on our system are working, more or less like on Grace. We have 5 logging nodes, right? Logging nodes, you can log in and do your stuff after you get everything compiled. You need to submit your job to the backend. The backend is a really workforce that has 300, I forgot how many, several hundred of nodes. Each node has multiple GPUs. All the nodes are connected with network, high-speed network, 40 gigabytes, at least, gigabits, gigabps network connection. And for now, that's probably even faster than 100 for some of the clusters. So each one is this individual computer. Just consider that, just like your laptop. Each laptop is responding to this big block here. You can have my laptop and your laptop collect together. You can do jobs together as long as they know how to communicate. You need to set up some communication between them. I taught a course 3 years ago about how to build a student cluster, just build this cluster. So what I did, I bought 20, 50, 20, 30 Raspberry Pis and give it to all the students. So they work on it, set things up. I brought a wireless router in the classroom so they can get together and build out the cluster and during the semester. So they started with a small group, the small cluster shared among their small teams. And then we get a whole class together, and everyone just contributing to their computing power, the small Raspberry Pi to it. So we built a cluster of Raspberry Pis and we did some calculation. So for Grace, we have CPUs. This one we have a socket 1, socket 2. Every socket is just individual CPU. We call it socket because every socket you can have multiple cores inside each CPU. So you cannot just simply call it one CPU because the concept can easily be misused. So we consider each socket as like individual physical CPU, but inside CPU you can have multiple cores, core 1, core 2, and not this laptop, my laptop at home I bought recently is AMD CPU. It has 8 individual cores, physical cores, and 16 virtual cores. So this number is getting bigger and bigger in some high-end CPUs. So that's your CPU. But then again, you have another, you have a PCIe, connector connecting to other different accelerators. Xeon is some old, NVIDIA, Intel's product to compete against the GPU. Now it's not in the market anymore. FPGA is another, you can consider some other competitor for GPUs, but they are targeting different applications. There are many different accelerators you can leverage. So it's just like whenever you have any computing task, your CPU will be controlling everything. Whenever you need some task to be offloaded to the accelerators, you offload to whatever accelerator you have access to. So the programming model for this, that's what people mostly use. To fully leverage computing power for this kind of system. This, you could have 100 or 300, 1,000 nodes like this. The program model behind it is most people using MPI, called Message Passing Interface. So MPI will be managing multiple processes across the whole network, across whole cluster. And then on top of that, you can use each MPI process. In individual node, you can manage multiple threads. Each thread can control all these accelerators. You can have multiple accelerators. You can use CUDA, you can use OpenCL, you can use OpenSSE. We'll talk a little bit about that. You can use OpenMP. There are multiple ways to do it, but all of these are on the thread level. So it's under one process, but each one has their own way to define different threads. Like CUDA has a CUDA thread. OpenCL define different ways to manage their threads, and it's just more or less like that. You have processes and managing multiple threads, and then you can control all the computing devices. You can offload your task that way. So for the CUDA programming computing platform, I already mentioned that hardware, compiler, toolchain, the libraries, and then we have a programming language. And on top of that will be your application. So essentially, for us, we don't need to worry too much about this. That's managed by HPRC, system like HPRC. We don't get into details about this. We just use it. Unless you, like me, buy your own hardware, you set it up, you probably want to worry about how to set all those things. But in general, you don't worry about this. We don't need to worry about this either. Not so many people needed to know the details about compilers. It's complicated. It's not like a simple translator. You're thinking about translating one language to another language. This is a bit more complicated than a translator, even though usually people say compilers, it's just like translator. Translate our high-level programming language into languages like machine can read. But in many cases, this compilers toolchain is very, very complicated. You need to think about optimization, different strategies. That's the part you don't worry about either. So just assuming someone is taking care of it. Now on this side, it's again that's the tools we can use for development purpose. NVIDIA, they have their own IDEs called Integrated Development Environment for CUDA. I believe it's free, or you can probably download and try it yourself. But I haven't used that inside for a long period of time. They might have better things to offer. But again, you can easily use a VS Code or just any of your favorite IDE integrated development environment to develop your CUDA code. Visual Studio is a common choice on Windows, and on Linux you can use anything. You can use a text editor to edit your code as long as you're comfortable with it. Now on top of that, we have programming approaches. Programming language I'm showing here to the last here. It gives you the maximum flexibility. You can do anything you want with CUDA. You have the control of registers, control of the memory block, and everything. As long as you have access to a CUDA compiler, you can write your CUDA code. You have maximum flexibility. You can do a lot of things with it. OpenSSE is another way to do it. I'm not sure you're familiar. You guys are familiar with OpenMP? It's like you write a program like C or Fortran code. Okay, it's just regular C code, assuming a C++ code or C code. You can add some comment on top of some loops. These comments will tell the compiler, say, hey, this is a loop. Help me to do the parameterization. So these loops in the programming, in the compiler world, is called directives. Directives. So these directives will be taken as hints for compilers. Compiler will take this comments, more or less like it will be like a comments in your code. If you don't have compiler that's supporting all these directives, it will just be ignored by your compiler. Nothing will happen. So it's good. It doesn't really interfere with your original code. You just need to put some particular comment saying that, hey, help me to optimize this loop. So compiler, if it recognizes this directive, it will optimize your loop automatically based on the the optimization strategy and hardware available. So OpenSSE is it's something like this kind of comments that you provide hints for certain compilers. Not every compiler supporting OpenSSE, but at least as far as I know, the GNU compiler and also NVIDIA compiler and also I believe Intel. I'm not sure if Intel is supporting. Probably Intel is no. What else? The PGI compiler that do support OpenSSE directives. It's basically insert some comment, it will help you to offload your code to GPU automatically without you writing a single line of CUDA code, which will do this automatically for you. It'll give you some very quick way to port your code to GPUs, but you will have less control in the way how the code will be optimized. And not like CUDA, you can write it, you can control everything. But OpenC is more or less like limited control, but you have a maximum flexibility. Now, the last one, which I think that's probably the recommended one to do so-called drop-in acceleration. It's just using libraries. Consider CUDA, the NVIDIA guys, software engineers already developed a library to do the linear algebra stuff on GPU. All you need to do is just need to call the library, and that's it. So your code will be automatically moved to GPUs for computation, and whenever you get the results, it'll get back to you. And that's the best way to use the GPUs. Yes.
Can you give an example of such a library?
That's what I'll get into here. So we have 3 ways, as I mentioned: the libraries, OpenC, and program language. Okay, that's something I'm talking about. So first, we get into the libraries because finally we'll focus on program language. For the library, it's easy to use. It's a drop-in. If you already have the linear library, in many cases, you should have the same interface. The APIs will be the same. The way how the functions got written, even the names will be very similar or identical. Sometimes you just need to add some extra prefix, so CU or whatever, NVIDIA, NV, some functions, and you can directly replace your current function. Just rename the function and keep the arguments the same. And the library will automatically take your input arrays and data, and move the data transfer data to GPUs for the computation. And then after this is done, it'll get the results back to you. So it's called this so-called drop-in method. You can write your CPU code first and just replace the file or name of the function, and you're done. You get your code running on GPU. That's the most efficient way. But of course, there's only a few, not a few, just limited number of libraries are written this way. In many cases, you have to learn how to use libraries yourself. Well, I mean, the beauty of the deep learning and also, TensorFlow and PyTorch is that this kind of work is done automatically by the library, by the framework. If you're using PyTorch to write a code, you don't worry about writing any GPU code. It automatically port your code into GPU, and it can run on multiple different computing devices. It can run on CPU and GPU, and depending on how you do it. But that's more and more frameworks like that, like PyTorch, it's getting into hands of developers and make it actually much easier to develop a GPU code without writing a single line of C to CUDA. So that's also the reason why we don't have so many people here, because everyone else is probably learning how to use a PyTorch or some other tools. So lastly, performance. As I mentioned, it's tuned by NVIDIA experts. We tried many years ago. I was in a project. We tried to optimize our code to beat some existing work. After we tried like a couple of years, and one day someone just found a library developed by NVIDIA developers. They easily beat our 2 years of work, because their libraries that were just released a couple of days ago. Not a couple of days. They released it just right after we released our code, and someone found it and then we compare results. They like a double, triple our performance. It's just like feel so frustrated. After you spend years and optimize the code, and you couldn't beat them. They have access to all the hardware information. They have the top-notch software engineers to develop this. So it's kind of hard to beat the performance with the NVIDIA library. You can try, but it's always a uphill battle. So these are some of the libraries. This is probably the old slide, but some of them might be still there, some of them might not. But in most cases, I'm just trying to show here, they do have a lot of libraries you can directly use for a lot of computational tasks. For linear algebra, for random number generator, for sparse matrix problems, for this, I'm not sure it's MPP. We have signal processing. You have, some other, this linear solver, I believe. There's also FFT and many others. If you get to this website, you can see now it's like thousands of libraries developed by either NVIDIA or some third-party companies that are contributing to this, to the framework. So my suggestion here is, before you dig into CUDA, start looking into the libraries that are already developed by other people. And if it's from NVIDIA, it's probably almost guaranteed that the performance is probably the best you can find in the market. So this is one example. I'm just trying to say, if you're familiar with this, I believe this is a what's library? This linear library. I forgot the name. LabPack or I forgot either LabPack or another one. Probably this is a LabPack library. So this function is a standard function. If you can find it's open source and everyone's using the same interface. So what it does is it just do the sum of x plus p. You have A is a matrix, X a vector, Y is a vector, and you get a sum of X plus P. Okay. You do it, you input, you tell the code here, you need to tell this function what your matrix A is, what your X vector is, what your Y vector is. What you do, if you want to use a CUDA, this is simple, it's called, I believe it's a BLAS. It's one of the linear algebraic libraries. So what you simply replace that function to this function and then keep the same arguments the same and just replace the function. And the rest you need to do, you need to manage the memory, mainly because as we all learned today, when you try to do the calculation on GPU, you need to have a memory on GPU. The GPUs cannot run anything on your CPU memory. At least, at least you need to do some memory management. There is so-called unified memory that we can talk about a little bit, but the performance is usually not so good. So it's good to manage your own memory. So whenever you want to do something, copy your data directly to GPU, run it, get results back. That's probably the cleanest way to do it, and probably most efficient way to do it. So when you want to run this on the GPU, the first thing you do is to change the function name from the standard C library to CUDA library. The first thing you do, that's easy. Everyone can do it. Now, second one, you need to figure out how to manage the memory. If you want to run your, if you want to run this X plus P plus Y on the GPU, you need to make sure you have a memory allocated to host the matrix A, the vector X, and the vector Y. And then this function will be running on GPU, and you need to have memory allocated for them. So that's the analog and other things will be needed for you to manage the memory. That's a part of the things you need to deal with in CUDA. The next thing you do, after you get this done and get this one, replace the name, just replace the library and replace the library. Probably previously you all linked to BLAS, now you just link to CU BLAS, and that's it. You're just using this library to do your work, and it automatically offload your computational task to GPU, and things will be straightforward. Okay. This is a link to the NVIDIA CUDA tools and ecosystem. And again, it's just like getting to a zoo, right? You don't want to stay at some place for so long. You want to go around first. You want to figure out where your favorite spot is, and instead they're a bit longer. And just go there, just check out all the tools available and try to take notes yourself. And then next time you get there, you know where you want to get to. You don't want to spend your time, sometimes you probably want just to go through all the things listed there and just see whatever you can find and find something useful. So it's like a treasure hunt, right? It's a lot of fabulous tools over there in this ecosystem. Okay, second one is OpenSC directive, and as I mentioned, it's just like a comments. If you can provide these comments to the compiler can do this work for you. So this is a very, very simple example. This is the Fortran code, actually. This example is a Fortran code. If you're familiar with Fortran, it's easy. Otherwise, don't worry too much. Fortran, you have a program, which is like a main function. You define a program for your Fortran code. That's your entry point. That's like your main function. When you get in there, and you can write math for other theory code, you're dealing with other visualization, you can deal with post-processing here. But inside the code, most cases, most of computational programs, you need you can find a kernel, the numerical kernel that takes like 90% of at least 80% of your time. Most of the computing programs have similar structure. So what you do, you get to the place where you identify the hotspot of your kernel, hotspot of your program, more or less like a numerical kernel. You get there and insert some comments like that. The explanation symbol here, it's like a sharp pound sign in Python. It's a comment sign telling this is telling the compiler this is a comment. But if you have this, if this compiler recognize OpenSSC pragmas, it will take this as a hint, not a comment. It will not ignore it. You just take it as a hint and use that to redirect some part of the compiler to offload this computation to GPU. So that's what a pragma is, or this is called pragma or directives, and for compilers. So I tried some of this. It works pretty well for some simple tasks. If you don't have a lot of dependencies inside your loops, and if this loop is completely independent, this could be very easily done with OpenSSC. All you do is just insert this kind of pragma into it, and that's it. Your code will be automatically offloaded to GPU, and you just need to enjoy your life and relax. Get the computer GPU to do the work for you. Otherwise, you need to figure out how to divide the tasks. Make sure everything you're doing everything you're doing inside GPU will not depending on some other variables, inside other part of your CPU code. So that's the hard part in many cases. But fortunately for numerical computation, for numerical simulations, it's kind of easy to separate the numerical kernel from other parts. You can consider that more or less like independent modules, and you can deal with that. So this works for multiple cores, for many core GPUs, and also for CPUs as well. Yes.
So that area of code is referencing a global variable that's being modified in some of the program, like on another thread in the CPU. You would have a problem if you tried to use a directive like that.
Yes, if you have any variables that inside this block, depending on any global variables, other variables inside the GPU, CPU, you should be careful. There might be some synchronization blocking you to apply before you can get this done. Either you block your calculation and say, hey, let's wait for GPU to finish, and then we get it back. This will be reducing the performance overall, but sometimes probably have to do this. So global variables is a big concern for this kind of problem if you want to do the offloading. And also, if this part of code, depending on some other part of the code, sometimes things, if you do multiple threading, that might be interfering with each other. So that's one of the concerns for this kind of computational time. That's why whenever you do this, you have to put some blocking before it and after it to make sure there's nothing interfering. But of course, if you're pretty familiar with the code, you can do this probably asynchronously. Otherwise, it's probably better to put some block to ensure that you get all the updates from your other parts of your code. So that's actually the reason why this kind of method is not so efficient in some cases. Sometimes you probably want to be smart about how you rearrange your computational tasks. And this is not so flexible compared to CUDA itself. So CUDA, you can dig into the details and do the very fine grained tuning of your performance. But here, it's mostly about for loops, and mostly about for loops. So OpenSSC itself is standard, and it's easy, and it's open, actually. It's even though it's started by NVIDIA, as you may imagine, but there are many other companies joining this effort. AMD and Intel, IBM, IBM, those are big companies, big names here, but there are also some small company in this consortium for OpenSSC. It's really powerful, and as I mentioned, it's not only work for GPUs, but also work for CPUs. Many years ago, there was one computer in China that designed the old CPU. That's what I heard. They started by designing this CPU, and then when they tried to sync some programming model, they use OpenSSC to get started. It gives them a very big boost initially to get some application ported to their CPU, but it turns out it's not working well when you try to do a lot of detailed tuning. So that turned out they threw away OpenSSC and they developed their own programming model based on that. So OpenSSC has been used in some brand new hardware just to test things out. You can find a lot of applications for OpenSSC. And once in a while, you'll see NVIDIA or some national labs are organizing hackathons to teach students how to use OpenSSC to optimize their code. There was a big effort along that line because especially for students who have probably a summer position or have some capstone project, some scientists or some researchers go through some very old code to you for you to optimize the code on, port it on GPU. That's something people have been doing all the time in the last several years. I was involved in several of those projects. People are just say, hey, Jian, can you help us to port this code to GPU? The very first try will be just using OpenC. It's the easiest way to get started. If you see, okay, this do work and you do want something more, probably you want to spend more time to port this into GPU or using CUDA directly. If you just if you just want to get, less than 10 or 20 times speed up, OpenC should be sufficient in most cases. And this is, some examples people did with different, it sounds easy here, but actually it requires a lot of work as well. You need to be careful about the correctness of the code without, make any mistakes. And even though it sounds easy to add directives, but sometimes, it's a bit more involved to get that done. So lastly, that's the programming language, which gives you the maximum probability, flexibility, but the problem is it's hard. You need to deal with very low level programming, pointer wise. You're not dealing with large scale array wise. You're dealing with pointer wise problems. You need to figure out how to do the alignment, how to do the pending, and to optimize the caches. That's the thing you need to worry about as a CUDA program. So there are multiple rampers on CUDA, so like a PyCUDA and some other CUDA best. So PyCUDA can use a Python-like library to run CUDA code, and there are multiple, not just one. There are multiple efforts to do that. One of them is open source. Another one is developed by NVIDIA. So it's your choice. You can take a look. And OpenCL, there are multiple ones to use OpenCL. OpenCL is kind of similar to CUDA, but just like a lot of names, terms are different. But the structure is very, very similar to CUDA. If you learn how to do things in CUDA, learn how to do OpenCL is straightforward. Vice versa. Yes.
So OpenCL support other GPU types?
Exactly. That's the power of OpenCL. OpenCL is supporting CPU, GPU, everything. You can do, if you want to do CPU, GPU programming altogether, OpenCL might be the tool you want to use. So you can.
What do you mean altogether?
So you can have OpenCL to write a set kernel. This kernel could be launched on CPU and GPU based on your requirements at the same time. And CUDA cannot do that, cannot do the job launching on CPUs, but CUDA can do job launching on GPUs. OpenCL can do job launching on CPUs, GPUs, and FPGAs, all the other accelerators. So you can consider like all the new vendors in this market of accelerators, they're supporting OpenCL by default, most of them.
So I cannot call like CUDA kernel from C++ code.
You can, but you cannot run it. You cannot run your CUDA kernel on CPU. I'm not sure. I'm not sure. Someone mentioned about probably they are experimenting this because you're. But again, it's depending on how CUDA runtime is managing all the hardware resources. If CUDA runtime can manage so FPGA can provide all the mapping, to the hardware counters or registers about whatever they do with GPUs, you can probably do the same thing. But it's not. That's not NVIDIA's interest, right? So NVIDIA is focused on their hardware. The reason that they have CUDA is they want to sell more GPU cards, NVIDIA GPU cards. But AMD is a newcomer here. AMD is pushing pretty hard on OpenCL. The same for Intel. Intel bought a FPGA company a couple of years ago, and they are pushing hard on the FPGA market. And they also have their own GPUs now to do something just like what NVIDIA GPUs are doing. So software wall is keep going, which is good. For developers, you have multiple choices. Right? You don't want to have one window to lock into your system, and you want some choices, which is always good. Competition always good. A healthy competition. Yes.
Does OpenCL talk to CUDA at some point in time?
That's a good question. It's not only talking. There's a lot of tools can convert OpenCL to CUDA, CUDA to OpenCL. So they can interchangeable in many cases. The structures are very, very similar. It's just like the way the name things are different. One is called a kernel, another one probably called a work group, or I forgot the name, worker. And one of them is called grid, another one called a work group. There are different ways, but they are conceptually the same thing, but they just call it differently. Once upon a time, NVIDIA was a big contributor to OpenCL, but they decided not to pushing hard on OpenCL. They're developing the focus on the open CUDA environment. So there's another one, I think it's called a Thrust, which is, I believe NVIDIA is pushing, also helping with some of the development here. So Thrust can do, I'm not sure the current status. You can check out the latest development at the Thrust website. But it's supposed to be supporting Intel TBB, which is like Intel's version of CUDA. You can consider that point. It's supporting CUDA, it's supporting OpenMP, and which is seems to be it's trying to unify the different architectures so that you can write one code that can run on multiple places. With it's easy, actually easy to write some code to run on multiple places. But if you want to make your code performance portable, it's hard. I'm not sure it's make your code portable easy. You can write your C code. It can work on multiple places with a little bit variation here and there. But now, if you want your code to have a performance portable, you need to be careful about how your code will be optimized, like a for loops, how that for loops could be unrolled or fused to match with the caches available on particular hardware, so that you can maximize the usage without overfilling all the things and getting all the racing conditions, etc. So that's a hard part. But again, get your code really working, like what the Strut is doing. It's actually it's kind of interesting. I haven't done much with Strut myself, but I know it's there. It's actually a choice if you want to make your code more portable across multiple platforms. So I list some of the information here, and you all can take a look at it. And Mathematica, MATLAB, they do have wrappers for CUDA as well, so you can try things out yourself. I think we can take a short break now. It's about 1 hour, and then next I'll just show you all, get it back to the CUDA code on Grace, and we'll get you all started. Quite amazing. Okay, let's get back to learn how to do the CUDA stuff on Grace. I already showed you how to get started. We have some examples running, and so I probably created this a while back. So this is a shared software environment. The module load here will just make sure whenever you log in the system, you have the corresponding software you need to do your work. And this software environment is working not only for the login node, but also for the computing node. So that's why whenever you submit your job, you need to run this software loading function or command line in your script, so that whenever your job is submitted to the computing node, the computing node knows which software you're using. We have like thousands of different packages. You need to be very specific about which particular version you're using. That's why when you try to load a CUDA, sometimes it's confusing, because by default, CUDA is pointing to the latest version we have for CUDA. Whenever you do some real world, the production level of development, you want to be very specific about the versions. And especially when you're dealing with Python, you probably know it. Different versions sometimes give you some problems. So that's a module load. That's a shortcut for module load, ML module load on CUDA, that get your environment set up. That's the first thing. The second here is to get your code ready. You usually get started working on this login node. As I mentioned, only the Grace 1, Grace 2, and Grace 3 have the GPU card, the NVIDIA cards. The Grace 4 and 5 are probably CPU only. I believe it's CPU only. You cannot do any CUDA runs, but you can probably compile your code, but you cannot run your code on those two testing nodes to test things out. After you get code compiled, you need to add it to your job script. There is a job script. We are using Slurm. Just a step back a little bit. Grace is a shared system. It's not something you can just run and wait and get the results back quickly. You need to get yourself into a queue, right? So a queuing system. That's when you get to Walmart, you stay in the line. You don't want to cut off, right, other people's place. And also different applications have different needs. Some people probably reserve 100 nodes just for the job. Everyone will have to wait. That's basically, first in, first out kind of policy we have here. Unless you have some priority. If you are doing hurricane simulations, the hurricane is coming, you'll definitely get the priority. We'll put your job to the very first. But in many other cases, just wait. You have to be, following the courtesy protocol. So after you get your job prepared, what you do here, you don't need to run your job on your local machine. There's one special queuing system called a Slurm. Slurm will take your job script. This job script describes how much resources I need. If I want to reserve 5 nodes with GPU, say A100 unit, and each node I want to have 20 gig of memory at least, I can put that into my job script, and I send the job script to Slurm system. Slurm will take my job system, take my script, and find the system available for me. If there's no resources available at this point, it will put your job into the queue, and wait until the resource is available. Then it will be your turn to run your job, and the results will be written back to your directory, scratch space, and you can just go there and download the file, and that's it. That's a whole loop. So again, the software here needs to be very careful about what software you're using. After you get everything tested on your login node, you can use the same software environment in the remote computing node. But you need to run this ML CUDA in your jobs. I'll show you the one example. You'll see what I meant here. So the login node is just for testing, development purpose. You're not supposed to be running your jobs there, because just imagine if you have 1,000 people using our login node, there's no way nobody can serve everyone. So login node is most for debugging, sometimes for debugging purposes, for running, for compiling, and for other simple tasks. Okay, so let me switch back to this. I believe it's already. Oh, it's still there. It didn't log me out. That's good. So if you if you're not familiar with all the editors, I believe there's a Nano, right? Okay. I'm using VI mostly. VI, it's like I'm not sure. It's like a weapon for Linux developers. If you're getting on any system, sometimes you may not be able to find some software you need, but VI is almost always there. So VI is an editor used by Linux developers. Let me see. I'll show you VI first, and then I'll show you. There's another one called Nano, which is relatively easy to move around, move your cursor around, and do auditing. But VI, if you're familiar with it, it's probably the best way you can do the editing on computers. There's also another way. I'll show you another way. So this is a job script. Actually, it's not showing all the things here. That's probably a problem with VI. Let me see if I can do this with Nano. It's the same here. It's probably the problem with okay, as you can see, actually there are some more lines here, but it's not showing up, but it's fine. Nano is relatively easy, but it's Control X. Let me see if I can go to another way to do it. I go to the files, go to my scratch space. So it's under my CUDA directory. That's probably the easiest way for those of you who are not familiar with the system. So I can go to my Hello World directory. I can edit. I can open up this file. So the top part is about the request I want to send. I want to. Let's go through this line by line, quickly. The first one is just name. You can name anything. I call it CUDA example. You call it anything you want. And the second one, time, is about how long you want your job to run. Because for our system to queue your job, we need to know how many cores you need, how many GPUs you need, and we also know how long you want to run it. So then we can put your job to the particular queue. We have multiple queues on our system. Someone's reserved for long jobs, someone's reserved for small jobs, for quick turnaround. So different applications have different needs. So we have multiple queues created. It's just like when you go to Walmart, there are multiple lines, not just one line, right? Different lines have probably, sometimes lines have 2 or 3 registers helping you. Some lines have only 1 people standing there. So it's a similar idea here. We have different queues for different applications. So you need to tell us how long you want to run your job.
Possible to leave that parameter blank? Like if I want to.
The default, there'll be some default settings there, but default setting usually, you want to be specific in many cases. Sometimes, For default one, probably half an hour or something. I need to confirm, but in many cases, probably your job probably need more time for that. You can specify a number of tasks, and also memory, how much memory you need for a node, and you can specify your output, what you want for your output, and you also, this one is kind of, wait a second, what I'm using, I'm running on the T4, which is using a T4 node. It's a GPU T4. I request, it's probably not on Grace. I think something's wrong here. Grace also has a T4 there. Do we have a T4 on Grace?
The node is a GPU.
Yeah, it's a GPU node, but it's a T4. It's a GPU card, special card. It's used for inference, not for training. It doesn't have a lot of memory, but it's still sufficient for running some simple inference problems for machine learning tasks. But I'll double check that. Don't worry. I'll double check with output here.
Yes, we have a T4.
Okay, so we do have a T4, so it's good. So it should be working. And then the partition here you need to specify is a GPU partition, because we have also CPU partition and GPU partition. And which, if you want to just run on GPU partition, if you want to run a GPU job, you want to use a GPU partition. That's a requirement. I think this one is just for training, testing, and sometimes we have special reservation for training purpose, so you have a priority if you have special reservation here reserved for you. And again, these are the ones we launch. If you have only one pound sign here, that will serve as an instruction for the CUDA job. If you have a double or more than one, it's just a comment here. I comment out these 4 lines here. So if you have an account number, after you get familiar with the system and your supervisor or yourself, you can write an application. For students, you need someone to assign an account for you. You can get up to multiple million of SUs if you're working in a big research group, you're doing a lot of content stuff. Your PI or supervisor can write a proposal to get multiple million of computing units. You can use them. So this account will be allocated for your particular research team. You can use it. Multiple users can use the same account to share their computing units. And you can also get an alert system. So get alerts from our system. Whenever you can do, mail type could be, or could be just get some error happens, or whenever something else happens. But by default, if you put all here, whenever your job is killed or finished or anything happens with the job, you'll get an email message. So this you can put your email address here. So actually, for our job, we only have 3 lines. So first one, I just do the purge. Second one, I do the module load, just ML will work fine. So purge will clean up your current software condition to just make everything perfectly clean. So you don't need to worry about any residue modules you forgot to unload, and just give you a very clean software environment. That's what we do. It's a common practice. Secondly, you can do module load. I specify a very specific version here, but you don't have to. But in the future, I probably want to pick particular version, just stick with it. Otherwise, if our system upgraded to a newer version and when you do the ML CUDA, it will probably load the latest version here. Might not be the same as the one you use for development purpose. That will sometimes cause problems. So finally, just run your program, and that's it. So again, the job script is very simple. First, the top part is just your request, how much resource you need. Second one is about the loading the environment, get your software environment ready, and then just run it. And not more or less. It's it should be straightforward. So I'll just do a very quick submission here. I'll show you all. Okay, let me clean up. CLER will clean up your current view. So what I'll do, I'll just do sbatch. Sbatch is a command to submit your job to Slurm. I'll do Grace. I'll show you what the Grace is. Let me see. So this is my job. I'm using this kind of different. I modify a little bit, and you can see I changed the job name to CUDA example. I request 30 minutes. The task is just one. I request a little bit because I don't need much memory. I only need request a 2.56 gigabytes of memory, and I just request one GPU, and all these others the same. I do the ML purge, and I'll just load the specific version. That's the latest version of CUDA, actually. So what I'll do as batch, and my job, which is Grace. So what it does, it will charge me because it's a shared system. After you get your account, you'll get some balance of SUs in your account. Just like when you're using a cloud computing system, you have some balance credit. So I have probably 100,000 SUs. I already had, I didn't run much, and I used already 0.5 SU. One SU is one service unit, which usually is just, if you're running one node, no, not one node, one CPU core per hour, that's one SU. So I'm not using much. So it's very, very, just imagine how many jobs I can run here. It's a very small job. And okay, there are some other instructions at the bottom. And let's see what else I can do. If you do the Q status, I think it is probably canceled for something wrong here. I submitted to the job C here, means probably this is status. It's probably canceled. Let me see what's going on. So the output is here. It's showing up with a job ID. As you can see, this 910 number is the same 910 number you can see here. That's my job ID. So my output is set here. I can do cat CUDA. Oh, actually, it's already finished. So it's not a cancel. It's probably just it's done. So whatever you have, it will output to this file. To whatever you write to the standard output, will output to this file. And that's your output for your job. If you are writing to a file yourself, the file will be saved into the directory where you submit your job, or whichever directory you specify in your code, right? You can write it to a specified directory, and it will dump all the output to a particular code. Okay, so that's enough for all the things. And let's get back to CUDA. That's the reason, the reason I think we really reserve a little bit of time for CUDA, mainly because in many cases you probably don't need to write CUDA. Learning how to use our system and get started with libraries is probably the most important thing. If you have any training in C and C++, using CUDA is just learning how to use a library, and that's all. So CUDA itself is an architecture. It's not a program language by itself. It's more or less like sugar added to C or C++. When I say sugar added, it's like extra features you can add to C and C++ based on the syntax C and C++ already have. There is a very small set of extensions to it to enable this heterogeneous programming. You can do the kernel definition of kernel functions and launch those. Those are the very small changes to the existing standard in C and C++. And also the APIs are very straightforward. Application programming interface is just like in the functions that define, you can easily get a document and look into all the functions that functionalities they are providing. And to manage all the devices, memory, etc., it's straightforward. And you can see from the examples I'm going to show you today. So as I mentioned, it started many years ago. When I was still at Louisiana State University. Our team got probably first a group of some Tesla card for testing purposes from NVIDIA. That's in 2008, 2009, around that period of time. I remember we got a card and we got a Sound Solaris workstation. And we put the card inlet and did some calculation. And one of my office mates, he's doing some black hole simulations using NVIDIA card. That's one of the very first CUDA version of black hole simulator. He developed this in that small office. It's quite amazing. And in 2007, I believe, 2007 they released the first generation, but we got our testing card in 2008. That's towards the end of 2008, we got our card. And this the major difference between CUDA and OpenGL is that the way how they define different things to manage their systems will be different. Shaders, textures, they're still there, like texture memory, it's still there in CUDA. but the majority of the terminology used in define different hardware resources, software architecture will be different. And we will learn a bit more about what they are called in CUDA here. They're called threads, grades, blocks, all the kind of thing. Now back then you're calling OpenGL, I'm not sure, shader, and what else? Texture and parameter space, whatever. They call it differently in the different ecosystem. So the current latest level one is a 12.2.2.2, and as far as I found out a couple of days ago, it's still the latest version. And on Grace, as you just saw, we have the latest version of CUDA installed on the system. So it's we're getting the latest version tried out today. Okay, so there are some major terminology and you get yourself familiar with. In CUDA programming, there are two concepts. Like one of them is a host, another one is a device. Host and device are referring to different things. You always need to keep your mind clearly. Whenever you're running your job on a host, on a device, they're separate. You need to manage the memory differently. You need to handle the data transfer separately. So just think you have two systems in your mind when you're running CUDA code. It's not always on device. It's not always on host. It's always a transition between two memories or two computing devices. That's what I would say. Okay, don't worry too much details, but you should, after you get the slides, you can look into the details there, but it doesn't matter. What I'm trying to show here is that how real-world application could be divided and offloaded to different computing devices at different times. So these are the serial code that you cannot easily parallelize it, and you cannot easily run it on GPU because there are a lot of if-else conditional statement. There's some initialization need to be done. That's the part of a job should be handled by CPUs. So there are a couple line of code, or in most cases not so long, or probably a function that will do a lot of work for you. So that's your parallel function. You need to figure out where to offload it to the GPU. And then you have some other serial code to summarize, to do the post-processing, to do the output, to take care of the I/O, etc. So for the serial code, it will be handled by CPUs essentially, and then you get your parallel code moved to NVIDIA code to GPU, and then finally you get your CPU handle the serial code. So if you are running your code from scratch, that's more or less like structural. If you are going to port the existing CPU code to GPU, you need to identify those parts yourself by running some profiling. I'm not sure you guys are familiar with profiling. For profiling, more or less like with a profiling, which is like it's a process for you to estimate or measure how much time a particular function is taking for you running your code. When you do this kind of porting, the first thing you do is to do the profiling. Then you have a rough idea about which part takes most of the time in your code. And then that's the hotspot in your code. That's the part you want to spend most of your time into it. You don't want to spend many hours just part of code that takes only 1% of your time. That doesn't make sense, right? The very first thing you do to do the porting, to do the profiling, there are a lot of tools in Linux that can do that. gprof and many other tools. You can sort of gprof and some other tools. You can easily profile. You can easily estimate how much time your CPU code is taking for you to do the calculation for different functions and how many times this particular function was called. And some of them are doing sampling. And give you some estimation. Some of them do the direct measurements about how long this function is running when you're running this program. So profiling is like the tool or process you want to go through before you start with the porting for your code. So this shows a simple processing flow. You start by running your code on CPU. So CPU has this connection with GPU with a PCI. You all know PCI. It's a what's this PCI? It's a common interface. What's it? The P? I forgot what the P is. Programming common interface or the P? I forgot the P. But GPU and CPUs are connecting through this the bus, and this PCIe is providing the interface for CPU and GPU to communicate. It doesn't use network here. That's using PCIe, which is much, much faster. That's probably fastest communication that you can find in a computer, the PCIe communication. So the first thing you do, you copy your data to the GPU. Because the GPU doesn't directly take the data, you need to copy it unless you're doing the unified memory, and we'll talk about it a bit later. But the first thing you do is you copy your input data from CPU to GPU. So then the GPU app code knows where to get the data, because the GPU code can only find the space, the memory space defined in the GPU VRAM. Unless, if you don't do that, the GPU won't be able to find the code it needs. And secondly, you load your GPU program. That's your kernel. That you launch your kernel. Whenever you do the offloading, the function will be copied from CPU to GPU. So that's a part where all the calculation will be getting started. You load your data here, load your function there, and whenever you want to run a job, the function will find the corresponding data in your GPU memory, load it back to the GPU for the computation. All these cores, GPU cores, will do the job for you. After you get the results calculated, everything will be sent back to GPU directly by the GPU program. Again, GPU program doesn't directly talk to CPU program, CPU memory. So the GPU program can only talk to GPU memory. And then when they're done, it'll copy all the data back to, that's your job. Or if you use unified memory, it will do this synchronization for you. But in most cases, it's probably better for you to handle this communication yourself. Now, it's if you step back a little bit, you think about this. You get something figured out that you need to be uploaded, write a code, copy all the input data to GPU, copy your program to GPU, launch it, get GPU calculate the job, calculate the whatever needs to be calculated, and then copy data back to CPU. That's a whole workflow, whole one offloading workflow. You can repeat this multiple times. No one is preventing you, how many times you can do this as many as you want, but every time you want to make sure the computation you're doing here is long enough to offset whatever time taken to do the data copy. Otherwise, the majority of the time it will take just copy data back and forth. Every time it's doing data copy back and forth, there'll be some initialization to set up the communication. There'll be time taken to copy the data and time taken to wrap things up. This communication is cost, this latency cost. Even though the data might be not that big, but every time there'll be latency, a millisecond or microsecond, but it's still not a time when you're talking about copying data back and forth. So that's a overview, more workflow. But again, the memory copying could be automated in some way. If you can define your array in CPU as a unified memory or managed memory, CUDA can check to see if this particular chunk of memory got modified. It can help you to copy data directly between CPU and GPUs. But sometimes, in some special cases, you want to make sure you need to force a synchronization between this CPU and GPU memory. So whenever you want to do something, separately. I'll show you what I meant in a second. So CUDA 6.0, now we already have a CUDA 12.2. But back then in 2014, when CUDA 6.0 was released, the unified memory was first get supported, just on the software level. There was no hardware support. It's just like CUDA will use the software to check if some part of the code and part of the memory was modified, and it will help you to manage the data transfer automatically for you. That's what CUDA 6.0 was doing. In 2016, in the first generation, I think that's a Pascal CPU, that's a P100 or whatever. Back then, it's able to support some caching and copying mechanism on the hardware level. So it's able to do things more efficiently because the hardware support this kind of synchronization. So software instruction will help you to manage the data, but the hardware will help you to make this operation more efficient. So now, all the new GPUs that do support unified memory on the hardware level and the software level, so which make it more efficient and probably, that's probably make it more more like a default choice for many programmers. So manipulative memory, instead of using malloc, malloc in C, when you dynamically allocate memory in C, you need to use malloc. CUDA malloc can do this for you automatically using the CUDA memory. But there is one extra function called the CUDA malloc manager. This will define a particular block of memory that's managed by CUDA. And this memory could be a bigger one that could be shared between CPU and GPUs. Both your CPU and GPU will see this memory. Virtually, it's not like physically they can see it. It's because CPU can only see the memory in CPU, GPU still can see memory in GPU, but through this, they can create a virtual managed memory block. Then whenever anything changes on the CPU side, there is a runtime function, runtime library can make sure that your data is synchronized between CPU and GPU. So that's how it's called a managed, even though physically GPU still can't really see the GPU memory, but this unified memory thing, it's like virtual memory for you to see, to make sure the CPU and GPU memory are synchronized. Okay, so that's some basic concept. We'll go into some details later. So this is a very simple program. The first one, the one to the left here, it's a C code. That's a hello world C code. It's just, of course, there will be include standard IO function. Otherwise, printf is not defined when you're trying to run it. That's probably the very first code when you're learning C or C++ to write as a hello world word. So NVIDIA compiler, NVCC can compile C code by default. You don't need it to be a CUDA code for this compile. You can call it .cu file by itself. Itself doesn't use any CUDA functionality. It's just a standard C code. You can call it .cu and CUDA will compile it and it'll generate output. You can run it. It just print out a hello world. Yes.
What if I give it a CPP file?
It will compile just like SAM.
Okay.
It doesn't matter as long as it will parse your input and it is treated as a C file, CPP file. So it's NVCC will handle all the extensions, different extensions. Of course, you can try it out in a second after you get to the website. So CUDA NVCC can be used to compile programs, with no device code. It's just by default it will fall back to a C or C++ compiler. And now this is a hello world with a device code. This device code is just dummy code. There's nothing in it. But even without nothing in it, it's a real CUDA code. It's a functioning CUDA code. So what we did, we define a so-called a global function. We'll talk a bit more about this, what global means. Called my kernel. That's the kernel. That's a kernel will be launched on GPU to do all the computation for you. There's another triple brackets here. It's the introduction of by CUDA, by NVIDIA to launch your kernel in certain way. So let's just say my kernel is still, if you don't worry about this, let's just forget about this triple bracket. It's just my kernel function, like the one defined there. But this one, what's inside here, defines how my kernel will be launched on my GPU. I'll tell you a bit more in a second about what is 1.1 means. But this is a kernel launching statement. It's not a simple function call. You can consider this like it's a kernel launching. And the kernel is defined here. And this could be, this is empty, but we can inside. It's a very simple code. It doesn't do anything particularly on the GPU, but it starts launching kernels, and it's a dummy kernel. Okay.
This would be a dumb question. The GPU can have one kernel at a time, right? GPU
can you can launch. That's a good question. Back then, you can only launch one kernel at a time. So GPU will help you to have a queue system. If you have multiple kernels sending to the queue, you can have CUDA runtime will manage all the jobs, all the kernels for you. But nowadays, I think depending on the size of your kernel, how big you're requesting, how many resources you're requesting, it's like a queuing system. We're doing the Slurm, right? Whenever you request a resource, you need to tell, like 1.1 here, actually more or less like you're asking how many cores I want, how many kernels, how many threads I want. So if CUDA decided they can fit your kernel here, it can at the same time, if it has extra resources, it can feed multiple kernels at the same time. So it can run multiple kernels at the same time. But back then, all the kernels will be queued up, no matter how big or how small your kernel is. But currently, the latest version, I forgot when they started doing this, but you can have multiple kernels as long as they fit into the requirements. Just like, you know, when you're submitting a job to our grad system, if you request 100 nodes, another probably professor requests 100 nodes. But we have 200 nodes here. We can fit your job at the same time. Both of them can run at the same time. So that's the current setup for CUDA. So you can run multiple kernels at the same time. And I believe NVIDIA has this controlling command. You can control how you want to do this. You can still go back to say, hey, I only want to run one kernel at one time, no matter how much resources is needed. So we got two new things, right, compared to the standard C code. The first thing is this global keyword. That's a CUDA keyword defined to indicate a function that it runs on device and it's called from the host. So always, as I mentioned, when you start writing CUDA code, you need to divide your brain into two parts. One of them is thinking about device, and one is the host. You need to always think about how they interact. Global is a function you can define in your CUDA code, but this global function can run on device, but you have to call this CUDA function. You have to launch it from the host function. Now, as you may imagine, you can have a device function underscore device underscore. That's a device function that runs on GPU, can only be called on GPU. Does that make sense? So that's why whenever you get this mixture of CPU and GPUs, you need to think about how you want to call them. You can also define host. If it's a host underscore host underscore, it can only be run on the CPU on the host side. And as a device, if you have an underscore device, it can only be run and called by the device on the device side. But the global, it's kind of like it can be called by the host, but it can only be running on the device. So this one is most commonly used for offloading your task. You can define your kernel on your host. You can launch it on your host, but it will be executed on your device. That's how you do the acceleration. That's most important keyword that you will be using a lot when you define your kernels. So my kernel is a kernel function, and then the host function here is a main function that I'm showing here. So this one is a host function. If you don't put an underscore host in here, that's by default it's a host function. So main here is a host function, and NVIDIA will be compiling this host function by some other compilers. It could be using some GNU compiler or Intel compiler and some other compilers on the host. But it will translate all the device and global functions using its built-in compiler. So that this will be compiled into so-called PTX code, and it could be running on, could be further compiling into into assembly code that could be executed on the GPU. So there's one more thing here. In addition to global device and those indicators for the functions, CUDA also introduced this triple angle brackets, which is making this host. It's trying to make a call from the host to device. It's like usually it's called a kernel launch. It's a bit more than just simply just call the function. It's trying to call the function and it's trying to launch the function following the instructions in this triple branch. We'll talk a bit more about that. So that's all. I mean, compared to C and C++, that's all what CUDA is introducing.
Really, that's it?
Yes.
Well, how do we get the data back from the device?
There are many other runtime APIs. You can call functions just like you are calling functions from other C libraries. So all the other functionality provided by CUDA will be through API calls. But these are the new syntax, which is different from C or C++. A standard C or C++ compiler wouldn't be able to recognize this. If you put this into a C++ compiler, it just give you error saying, this is illegal syntax. But CUDA compiler can recognize this. It will understand it, and do the things for you. So that's the only new stuff. Just one of them is a kernel definition. Another one is this triple brackets for launching the kernel, and that's it.
And the signature of the kernel, does it always have to be a void and take no arguments, or it can have different return types?
Yeah, that's a good question. I believe by default it's supposed to be void because this doesn't supposed to be. You can always have a return value. I believe CUDA is handling this internally for the error handling and other stuff. But this, I believe, is supposed to be a void in some cases. But I believe you can also return, but depending on how this could be handled. In most cases, because you needed to manage the input and output arrays yourself. So you don't directly do the output through this function. You directly write to the particular array. You put it into the arguments inside here.
Okay.
So a common practice is you don't do that because when you return this kernel will be directly returning to the host function because this my kernel itself. It's called by the host function. It's a global function, right? It's called by host function. The host function will be getting whatever error message you are returning back to it, but not the data itself. Mm-hmm. You need to manage the data transfer yourself or use a unified memory management later. So this cannot do anything, but you can compile it and run it. Everything works fine. It's just, that's a starting point, which looks good. It's a device code and it's a dummy function, but we get all the procedure right. Everything is just working in this way, but we can add more stuff to my kernel function to do something more. So first thing we do, we can probably add two vectors together. That's a very easy example you can think of. And so we have we can define two vectors A and B, and we want to get C from the device. Naively, we might think, okay, let's say we have many CUDA cores. Okay, let's imagine we have many virtual CUDA cores or CUDA threads. We can have each CUDA core handling each one of these elements because for vector addition, every element could be done element-wise. You don't need to worry about the dependency between this element and this element because it's irrelevant. For me to get my C here, and for this number, I only worry about these two elements. So that makes it perfect match for CUDA cores. So each CUDA core can handle this operation once. Just imagine if you have 1,000, for example, 1,000 element in A and B, you get 1,000 output for C because you have to have a matching dimension to do this addition, right? Assuming you run this using 1,000 CUDA cores, it's just the total time taken for you to do this is just one addition instead of 1,000 addition. That's how you leverage the power of parallelization. Does it make sense? It's not like you need to do this one sometimes. It's just one addition, but it's just done all at once by 1,000 cores altogether. So that's the speed up we're getting. But the problem is to copy this guy from CPU to GPU, and copy this guy to CPU to GPU, and copy this back from GPU to CPU. Sometimes it takes some time. If your computer here is very easy, very fast, actually you'll see when you do this CUDA programming, if you're doing this simple task like this, you are taking much more time than just run it directly on CPU. The reason is that you're not saturating your GPU enough for you to benefit from the computing power. You are just wasting your time in data transfer. Right? So that's the major problem, the most important problem you want to consider, to put enough computation load on GPU so that you can offset, or you can ignore the overhead by spending more time doing the computation than just doing the data transfer. But you have to do the data transfer. That's the problem. So yes. Okay, let's get back to this simple program. Now instead of define a dummy function, now we have this AND function. So take A and B, and we get to C. So A could be a vector, B could be a vector, and you can see it's a pointer. Pointing always pointing to the very first element for your vector, and for element of your array. We do the summation. This will do the summation for you for the, for all the you can iterate through the number of elements inside your array. You can do this altogether. So this is just for every single element. Okay.
And it doesn't need to know
the size.
Yeah.
We will talk a bit more. The dimension will be controlled by something else. We'll see that. So as before, this global is defined as a global function. It will be, remember what global is? Do you guys remember? It's defined on the host, and it'll be running on the device. Yes, that's how you define this kernel here. So this add function just runs on the device. When you run on the device, you need to keep in mind, when you run on the device, A, B, C, these are pointers. They need to point to address in the device memory. Pointers are the place holding on the address, and you want to, the numbers are put into the particular address. And when you get play with this, addresses, you need to be careful what address you're talking about. Is a device address or host address? So to do that, we need to allocate memory on the GPU, on the device, to make sure our ABC have place to stay. It's just like visiting your friends, right? They needed to allocate a room for you, so then you get in there, you stay there. You don't carry your room with you. You go there, you ask your friend to allocate a place for you. When you're visiting when you're waiting from CPU to GPU, you ask the GPU to allocate a room for you, so that you can stay there and do your work. Okay, so we already talked a little bit about unified memory just as a concept, but here we need to do the hard work. We need to make sure we know how to do the allocation. So for CPU, when you do the dynamic memory allocation, you use a malloc, you use free, you do the mem copy. I believe there is a reallocate or some other functions like in the standard library that you can use to do the memory management in C and C, mostly in C. In C++, you do it differently. So these are standard C, libraries, and you can directly use. It's in a standard library, and you can directly call them. CUDA provide APIs in a very similar way. Its only difference is that you have extra CUDA here, but you also capitalize the first letter. In C libraries, all lowercase, and malloc, free, and memcopy, etc. So now, when we want to run on our kernel, let's first look at the main function. Let's see what main is doing here. So inside the main, we first define ABC as the host copies. That's where we keep our number. Here we're just doing, we are not doing a vector yet. Let's just think about one number. So we have ABC defined. These are three numbers. A could be 1, B could be 2, C could be 3, right? But C will be the results. We will initialize A and B. So then we define a device copy of ABC. We get the device. There's no reason why you have to use a D on the score. It's just some people prefer to put a D on the score to represent this is a device memory, so that you don't get yourself confused. So you define another size here, size of integer. Here is just depending on the size of the integer you are defined is just 1. Size of that probably just 1 byte or probably 4 bytes, depending on how big your integer is. For the integer, I believe here is just 1. I'm sorry, 1 or 8. I forgot. You can check the default size of integer. So allocate the space for the device copies of A and B. This is you do the CUDA malloc. You allocate in the same way. That's probably the same syntax you use for malloc. Anyway, so here it's just one address. One number. It's not a vector yet, but we do have the size defined here. Size is just simply 1 and representing one integer for A and B, C, etc. Because we are just defining one number. But this size could be more, so then you can deal with vectors. But for this very first example, we just deal with 2 numbers addition. So we get to set up the input value for the host. So next thing we do, we copy our data from our host to the device. And CUDA memcopy host to device, this is like a flag. You tell CUDA runtime that I want to copy my data from host to flag, host to device. When you get the result back, you need to copy device to host. So this, you can see that there's a difference here. Device to host, host to flag. This is like a flag to show the direction. And so that we can use the same function. This just shows the direction where you want to copy data from and to, but the same function could be leveraged. Otherwise, you'll have 2 functions. One function to copy to the device, and another function to copy to the host. But here we are just using one function, but with multiple, different flags to the end. just consider this as like a 0 and a 1, you know, it's a flag. It sounds like, you know, complicated, it's just a flag telling you the direction of the copy. And after we get the memory allocated, we can start doing the computations, and we launch this AND function. Yes.
Oh, that's right. We used CUDA malloc on the previous slide. That will declare space and RAM on the graphics card. Correct?
Yes.
Okay.
Yes. So DA and DB and DC, all these three will be pointing to a particular address on the device.
Why do we have double asterisks instead of just a single? Because we're doing
Yeah, we got. Well, I know what you're talking about. We'll cover that a bit later when we're doing the vector addition. This one is just number. You know, you don't worry too much about the size, because the size itself is representing the particular data type. Could be double, could be float, could be integer. So that's why this step is important. That tells not only the size for different data types, but also, you know, you can multiply that with number of data points you have. Could be 1,000, could be 1, could be 10. There'll be a multiplier there. But size of integers just give you the unit of particular integer that you're dealing with, because we are just dealing with integers here. If it's a floating point, you can have a float or double. Yeah.
Oh, so void asterisk is a range interpret cat?
No, void here is void to pointing to this is for address. This for address. This is for when we do the malloc. Here is you need to do the casting later on, but here is pointing to the address of address. It's like, you know, so here, as you can see, this is a reference, and then you are casting this to a double pointer, which will point to address, hosting the address, and that doesn't have any real, you know, it's just address itself. That's a void. Yeah. But that's you know, almost every time you do the same thing, unless your DA, DB, DC have different dimensions. But in many cases, it's good to convert all the data sets into one big array. You can handle all the multiple arrays differently. So this is almost always true. This comes down no matter what your DA is, as long as you have just one long array that you deal with. The malloc will be always the same almost. A DA itself is just one-dimensional array, unless you want to deal with different dimensions, but it's not recommended anyway. It's getting your code more complicated than necessary. So the kernel is launched on block 1 and thread 1. I'm talking about that. 1.1 here means the first block, first thread. We'll talk about that later. But the job will be launched to GPU. The GPU takes the data from DA and DB because it already copied the data to DA and DB, so it knows what DA and DB are, and then it will calculate DC based on the function you're launching. This is AND function. You'll get back to find what this AND function is. You'll take this DA and DB and get the results to DC following whatever you define in this kernel function. This one is indicating that my kernel will be executed on block 1 and thread 1. We'll get into that. So don't worry, just consider it's one particular location I want to run particular CUDA core or particular CUDA thread. I want to run my kernel. So that's it. But the rest is just your kernel function, same thing. After you get the results calculated, this will copy the data back from DC to C. So after that, your host will get access to your C, will be updated, and then as a good practice, you're supposed to be cleaning up your, allocated memory. Just like when you're writing the malloc, you need to free your allocated space to make sure you don't have any memory leak and reduce all the potential cybersecurity problems. Okay, so we just did a very simple addition of two numbers, but GPUs if you're just doing two numbers on GPUs, you'll be wasting a lot of your resources. It doesn't really worth it. You want to do big array addition, which will we assume when you're doing a lot of computations on the GPU, it will offset some of your time wasted in copying, right? So how to run the code in parallel on a device? The easiest way to do it is to increase this one of them to n. This n could be a very big number, so I'll get back to this later on. So that means you can do this addition n times at the same time. And it will greatly reduce the time taken for you to do the addition. You don't need to do this one by one. You can do this all together. Just with one addition, you get your job done directly. So let's try to do, instead of addition of numbers, let's try to do a vector addition, which is very, very commonly used in GPU programming. A lot of things you can do by vectorizing your operations. You can directly utilize CUDA to do the computation for you automatically. So let's get back to the addition function. Now is the fun thing of just getting started. This model function is no longer star C equals to star A plus star B. We are utilizing this predefined keywords. This is predefined. That's not something I come up with. It's something from CUDA. So block ID X, block ID Y, and X. And you may imagine there will be block index X, block index Y, block index Z to deal with three-dimensional thread blocks. Okay. So let's just imagine this like a predefined indicator to label all the cores, virtual cores, not real CUDA cores. All the CUDA cores you may have heard about, those are virtual CUDA threads. People call it virtual cores or virtual threads or CUDA threads. This is the same thing. All the CUDA threads are virtual. So it's up to the CUDA runtime to decide where this particular thread could be executed. Otherwise, just imagine there will be a lot of problem. If you are referring to a particular physical CUDA core, this core might be busy, this core might be occupied. How do you deal with it? So CUDA virtualize all this. By defining this virtual CUDA core or CUDA thread, whatever you do, the CUDA runtime will figure out a better way to allocate your job with all the resources available, which make it very easy to scale up your application without you to deal with individual, keeping track of the usage of the individual CUDA cores, physical cores. Now, just consider this. This block index, these are the numbers you put into the triple angle brackets. Okay, so now I'll get back into that. But now, what you're doing here, if this particular data point A and B, it's copied to consider this A, B, C, A, B, these are already vectors, not just one, two numbers. A and B are already vectors. For the first element of A, the first element of B, you are resulting on this block index X, which might be 1 here. So it will assign one virtual index for you, for your first element. If you move to the second element, this could be 2. So CUDA will automatically map your element to individual CUDA threads with this predefined index. So when you launch your kernel will have a fixed block index X, block index Y, block index Z, etc. And this, for individual kernel, it has a fixed one. But when you launch your job, CUDA runtime will allocate this number to you automatically. Even though you write down this as a constant, but for CUDA runtime, this will be automatically assigned to you based on the number of threads you are requesting. Okay, let's go to the example, then you'll see what I'm talking about. So that's our addition function, right? So I just call the blocks X, which is just a number. So if I allocate my, if I want to submit my job to 4 threads, for example, when I do the kernel launch, I have 4 1 in my triple angle brackets. By defining my kernel like this, CUDA runtime will get to the very first block X, which will be 0. Will copy my calculation directly by assigning this 0 to my corresponding block index. So my first element will be assigned to the thread 0. Second allocation will be threaded 1, but because the block index X at this particular CUDA thread is 1, so this block automatically pick up the addition for my first element. So every block here is an index for this block is already predefined. When you assign when you launch the job or launch this function to individual blocks, it will pick up the corresponding block ID from that block and then do the addition automatically. But to us, it sounds like like magic. But to every individual block, it's just hey, I'm block 3. I'm dealing with 3 all the time. Give me any kernel, I'll replace whatever inside this block, index X into my old index. This is my room. I'll assign this logs to you. Give me this function. I'll replace whatever you block index X is with my current block index X. This is like room 3, which will do everything in 3. So it will replace everything 3 here. It will do the addition for the third. This is the fourth element. Now you think about you have thousands of these blocks, and everyone keeps its own room, right? Handling the things. Whenever you assign it, it doesn't really care what kernel you have, as long as you tell me that. As long as I can identify in your kernel function, you have this particular predefined, number. I'll replace it with my room number. So by doing that, all this all the calculations could be done at the same time by multiple blocks, and each one will be handled everyone. Because each block is like each thread, but it's just defined differently. I'll tell a bit more about that in a second, but just consider every thread has this thread number, every block has a block number. It's just a different structure. You arrange things. The same idea could be applied to MPI, message passing interface, right? There is a so-called global context. And when you launch your job on multiple CPUs, and every CPU has its own rank number. Every process has so-called rank ID. So you're not directly managing all the process numbers yourself. You directly utilize the rank number to see which particular process you're handling. You are doing something here. When you launch your CUDA kernel, you don't assign your CUDA threads number yourself. You just give it to CUDA runtime. CUDA runtime will pick up the corresponding, constant for individual thread and assign that for you. So that's the magic behind all the parallelization for the CUDA launching, kernel launching. So let's look at the main here. So what's the major difference? For the main, now we are handling 2 vectors addition, right? So compared to the previous one, all these are the same. The only difference is that now instead of using size of integer, I have multiplication of n, because I want to calculate n integers, the summation of n integers. So the size will be multiplied by n numbers, which is easy to understand. Nothing changing here because everything will be handled by size. Size will be different. Good. I'll allocate a longer list for you. Instead of this 1, I have n element allocated on my GPU. That's good. But on CPU, you need to be careful because now you need, instead of this 3 numbers, you have 3-dimensional, 3 vectors. That's the standard way to allocate 3 dynamic arrays based on the number of n you define here. N is 512. So I allocate a memory block that can hold 512 integers. That's how this allocation is done. The reason this is void because it's a double star. This void just means this allocated output here is not pointing to the first element of the array. It's pointing to the address of the array, and that's a difference. So these 2 functions are, you can only easily copy. These are probably just randomly generated. You can define this yourself. You should randomly generate n random numbers in A and n random numbers in B. You can easily, do something else, but this is just a quick way to do some quick calculation demo for A and B. So nothing's magic here. Everything should be straightforward, except this part will be something you have to do when you're doing this GPU memory allocation.
Is there any limit for the number of entries in the vector to the end?
It's a huge number. It's to the let me double check the number. Okay, let me switch to. Let me show you this one. N is about this big. That's about, let me count. 2 billion, right? That's about 2 billion. So That's why we don't use a thread. Thread it has limitations. Thread maximum thread you can get only 65,000, but for blocks you can get to up to 2 billion, and this is all virtualized. And a thread is like you can consider. Well, let's go back to this. We can talk about this later on. 2 billion is probably the number you can use, the maximum number of threads. But again, there's no 2 billion CUDA cores for you to use. So you will be automatically queued up. If you have some tasks with a huge number of the huge number of arrays, it will automatically cut them into pieces. Everyone will be done part until it's filling, and then it will do this piece by piece. Does that make sense? So but it's handled automatically. So you don't need to worry about how you cut them into pieces to put into the computing core. So that's a virtualization, the beauty of virtualization. Where are we now? I think we are okay. So next thing we do, just like the before, like what we did before for a single number, we copy everything to the device, do the addition. The only difference is that when you do the launching, so 1, 1, you have n1. N could be up to 2 billion, or actually for 100. I'm not sure for the latest one, H100, probably more, I don't know, probably less. But this second dimension can only be up to 65,000, something like that. So that's why usually, you start with the second dimension. And this by example give you maximum freedom. This dimension can only go up to 65,000. Otherwise, if you go beyond that, you need to do the partitioning yourself. But if you use this dimension to increase the number of the calculations, the vector size, this dimension will give you very maximum flexibility because it's huge. It can hold all the data, hold all the virtual CUDAs you want to launch, CUDA threads you want to launch. After you get the results calculated, you copy it back. But again, remember the size is already scaled up by the factor of n, so it's a bigger. It's not simply copy the data from the pointer. You need to copy the whole array. That's why you need to specify the size as well. Make sure it's. Yep. So these are the three for C for the host memories, dynamic arrays. These are 3 for the device arrays.
Would it work if I replace malloc and free with the new and delete?
New and delete, that's a C++ syntax. It works.
Yeah.
Okay. Yes.
And does it work with like unique pointers?
Unique pointers?
Yeah.
You said that you mean the like C++ feature to define the I don't know if it's working that way, but if it's a standard feature in C++, I believe NVIDIA NVCC should be supporting those as well, because even though the example we put here is mostly following C, standard library syntax, but it's supporting C++. All the features from C++ should be also supported in CUDA as well. So nothing different from that.
Thank you.
We have a struct that we define at the beginning of a program. Could we access it on the device?
Yes, you can define structure. It's just like the only thing different is that when you copy here, the size will not be size of integer, it will be size of a structure.
Yes.
And now the tricky part is that there was always, when we talk about performance, always a trade-off between structural arrays and array of structures, right? Structural arrays, it's like easy to handle. Every array, you can handle them separately. You can easily do a very quick iterations through all the elements inside each array. But if you're talking about array of structures, every structure could have a complicated structure internally, and CUDA might not be good to handle those individual structures for dealing with data operation inside. So it's recommended if you talk about always, if your performance is your first priority, you probably want to deal with the structural arrays, so that every operation will be operating on individual element with a homogeneous structure or homogeneous array, so that your performance might be be boosting. But I learned that through the Best Guide book. It might not be the case nowadays, because this seems to be a very common request from programmers. They want to handle complicated structures. on the CPU and on the GPU, and I believe CUDA, the NVIDIA have been focusing on a lot on the optimization strategy. Like what I learned is just like something I learned a couple of years ago with some older architecture. But again, that's have some merit in it. Basically, if you handle homogeneous structure, it will be much easier for a system to handle those iteratively. Okay, let's get into what's the addition unit. Okay, now for unified memory, this example might not be a good example, but I think it's just similar. I'm doing something you consider is almost the same like what I did before for the kernel function, for vector adding. But if you have a managed memory for the values, you don't need to copy data back forth anymore, which is a beauty. But you need to make sure you do the so-called device synchronization, so that your device and your device and the host memory got synchronized before you utilize data for something else. So this more or less like a block, the block to synchronize your data and then move on to the future. If you don't do this, the data might not be copied back yet, even though it's supposed to be copied back. This one is not required, but it's recommended, because when you do this abandonment, your data could be sitting just on the device side, and your memory side, your host side is probably just empty. Without doing this and start doing something else, you'll get into some problem. You get a segment fault or something. This synchronization will ensure that data get copied back and forth. At least your GPU, CPU memory got synchronized. So this will managing all the copying, for your matter. It's just like save some couple more statement in your compared to the previous example. Help you to make sure your data is stay synchronized across devices and the host. So this is the one way you can do this. It's the same malloc. It's just like you have management here as an actual keyword. It's the same thing here, nothing different. But you don't need to do copy back and forth. So it'll save you a couple statement. There's another easy way to do it. Instead of doing malloc manage, you can directly define a global variable, which is actually, global variables are not recommended by many, software engineering books, but it's still highly recommended. It's commonly used in GPU programming, because on GPUs, every time you do the GPU computation, you put the copy data in, and after you're done, you copy data back. So all the global variables you define here would cause a lot of problems, because every time you do the computation, you get new data in, you get new data out. So you'll have something like that already managed by default. So this particular managed keyword will tell the CUDA runtime that this particular array is a managed allocated array. So this is probably the simplest syntax you can find for using the managed memory. So you don't need to define, you don't need to use a CUDA malloc to define an array. You can directly define a global variable, but with extra managed keyword on top of that.
What is CUDA device synchronized with?
CUDA device synchronized is copying your data back and forth. If you have data on the GPU, but you don't have data in the CPU, it will copy data to your CPU to make sure both sides have the same data. So you synchronize your device and the host memory to make sure they have the same copy. So whenever you define manage, you will have a copy of your CPU and GPU memory. You reserve particular, you'll reserve this big array on both CPU and GPU. Synchronization will make sure whatever latest change will be copied back to the to whichever hasn't been changed. So it'll keep you to the latest changes you made to your managed memory block. But you'll have two copies of data anyway, one on CPU and one on GPU. When are we going to end? Like 12:30? Oh, I'm not sure.
It's
okay. So, we have a lot of things to talk, but I think you all can, after you get to understand the basic principle of the host and device and memory management, copy back and forth, that's all. That's all you need to learn. Everything else is mostly about, be careful. Everything is in the details about how to manage a particular group of data and minimize the data copying back and forth, and then you can maximize your performance. So this is our best review. And we already talked many times about unified memory programming. And the only difference here is that I have one example. I think I already have this one. No, this is probably the same example I mentioned. It's probably already repeated. These are one more example using the memory. Last, I want to talk about managed devices. The reason this is needed, we need this part mainly because sometimes you may have a GPU node which has more than one GPU. You can have 2 or sometimes 4, even sometimes you get 8 GPUs in it. There are some special, for memory management, you manage this memory for individual GPU. You don't have unified memory across multiple GPUs. Every GPU has its own device ID. And you need to do this for individual device. And fortunately, there is a CUDA device that you can get individual device. If you are writing multiple threads program, every thread could be allocated to manage the individual device. So device ID is just simply 0, 1, 2, 3, just numbers. After you get your device ID, which is just function call away, you can allocate this particular device ID to particular thread. You can use this thread to control your device. You can then, that's your job to decide how do you want to divide your task into multiple smaller pieces, and each one could be launched separately on individual devices. And there are also, go ahead. No, I'm just saying there are also ways for you to take the big chunk of data, and there are some programmers, some libraries can help you to divide your task and allocate to multiple GPUs at the same time, without you to worry about how to allocate the computation. And PyTorch and TensorFlow, that do have this kind of functionalities for you to do this calculation and division automatically, partitioning all your problem automatically. Yes.
So people who build PC hobbyists who build PCs, when they get multiple graphics cards, the amount of VRAM they have is the least amount of VRAM they have in a particular graphics card. It's the minimum of all the VRAMs. Is that because the virtual memory is copying over to every single graphics card separately and then pretending it's one thing? Yes.
So if you are doing a slide, I'm not sure you are familiar with that. You can. There's always for some. I believe they get rid of this recently. But back then you can go a slide configuration. You can have 2 GPU cards connect to each other through the on top, very fast NVIDIA kind of thing. By doing that, these 2 GPU cards can share the memory, which is quite efficient for doing a lot of big games. If you have limited amount of memory, you can share 2 GPU cards memory for big tasks. But now they are get rid of the. I believe NVIDIA get rid of the slide configuration. If in that case, if you don't have this slide configuration with 2 GPU cards, that you need to copy, talk to GPU, CPU through the main bus. The bandwidth for the bus, for the PCI bus, will be the main bottleneck in many cases if you have multiple GPUs. But for high-end systems, they have so-called GPU direct, which GPU can directly talk to GPU. So GPU A can talk to GPU, can see the memory on GPU B, but this connection will be coming through the network, high-speed network. It's not through the PCI C, but also depending on how the motherboard was designed, there might be some support lately. Like NVIDIA, they have their own SMX cards, boards that can support communication between GPUs directly, which is not the case for PCIe cards. They have different communication protocols. But the bandwidth for the bus will be the bottleneck for you to efficiently communicate through CPUs and GPUs, because everyone will need to go through the CPU to get the data back. They cannot directly talk to each other.
Does Grace have a connection between graphics cards?
I believe Grace do have the GPU direct, but I haven't really used that myself, but I believe the network that we have does support GPU direct. That's kind of an interesting question, and we can if you're interested, we can get back to you with more details. Yes. So NVIDIA runtime, CUDA runtime has some error handling stuff like the CUDA get last. This is the one I commonly use. Report the error code together with some information. You can print it out. You can easily check what error you have, latest error you have. And if you have multiple devices, this is how you manage them. you first get how many devices you have. This is a device count, give you say 5 or 4 or 2, depending on the number of GPUs you have. Then what you do, you iterate through this number. If it's 4, you just iterate through 0, 1, 2, 3, you have 4 numbers. Each number will be the device. You can set a device to the number so you can control them. So that's very straightforward. Just play with integers, 0, 1, 2, 3 in most cases, but you can set the particular device to a particular number so you can control them, individual devices. And it's very straightforward. You can assign, as I mentioned, you can assign individual threads to control the individual device by mapping the thread to a particular device ID, and that's it. But then the tricky thing is that now if you want to control individual device, you need to handle how to divide the tasks. If you have calculate a vector addition of 1,000 element, you need to manually, but it's just in the loop, right? You need to cut that 1,000 into 4 pieces. Device 1 will do the calculation from 0 to 250. And then you continue doing this, right, to finish all your tasks. Just divide and conquer. And that's the standard way of doing the multitask, programming. I'll quickly go through this. I think that's probably, that's almost the end of the talk. So we didn't get into details about the blocks and the threads, but I do have some intermediate level of presentations about CUDA, and I'll share with you all about those slides. It's just like we just don't have the time for those. Previously, we have a whole day workshop for CUDA, starting from this to threads, blocks, and grids. We can manage all the CUDA threads, and to finally we launch some big jobs. But today, as long as you learn how to launch your jobs on grids, learn the basics of CUDA, you can get yourself started quickly. But again, I would recommend you start learning all the libraries instead of writing your CUDA code directly. Learning to use those CUDA libraries will get you started with the CUDA applications quickly. You don't need to start from writing a single CUDA code to build your application. You can do this in a more efficient way. But understanding the basics will be helpful for you to see how things are going. If you read other people's code, you'll know what's going on there. With that, I think that's all for today. I'll be around, for the lunch, and we can talk and chat about other things. Thanks a lot.